Hello everyone, my name is Binnar. I'm a subject matter expert in offshore software. Today, I'll be presenting a case study on the design of floating wind turbines using MOSES wind turbine. Here's today's content. First, we'll look at the overview of the project and then move on to the scope of pre-service analysis and what they are. Then we'll look into technical issues engineers encounter during this project. And then I will briefly introduce the functionalities of MOSES wind turbine. Let me start. Here's an overview. This is a basic design of a floating wind turbine owned by SK Ecoplant, a Korean construction and engineering firm. The pre-service designs presented during this session were performed by another Korean engineering firm named Gentech ENC, which also created this presentation material. I have obtained their consent presented here at this conference. So before the start, I would like to let you know what they did is one of many ways, and it does not mean that is the only one correct way. Also, it does not represent our intention. I mean, many users use MOSES in different ways. This is a semi-submerged type floater designed to support 10 megawatt turbine and its tower. The design is tailored for the sea near Ulsan area here, a region where many offshore wind turbines are expected to be installed in the future. This part of the East Sea is significantly deeper than the western coast, with a depth of around 70 meters. This is a semi-submerged type floater designed to support 10 megawatt turbines and its tower again. The columns are 33 meters high and 9 meters wide, with a spacing of 45 meters between them. The lightest weight of the structure is 3,247 metric tons, with an additional 1,305 metric tons for the turbines. To achieve a depth of 15 meters, 5,934 metric tons of ballast water are required, bringing the total weight to approximately 11 metric tons. For moorings, catenary type moorings are used with 142 millimeters studdless chain with a pretensions of 858 kilonewtons. The design scope includes all the activities from fabrication at the yard here to installation at the site. This type of engineering is called pre-service engineering. Specifically, as we know, the floaters are fabricated at this location and then need to be loaded onto barge from a fabrication yard. This process is referred to as load out analysis. Then lower to make it free flow using the buoyancy difference. During this stage, ensuring both structural integrity and hydrostatic stability is very important. Once the floater is at the sea, it is temporarily moored to the quay for the installation of the tower and RNA, rotor nacelle assembly. At this stage, it is crucial to maintain hydrostatic stability, both with and without the tower and RNA, as well as station keeping. After assembly, the floater is towed through the sea to the installation site via this path. Ensuring structural and hydrodynamic stability during the transit is essential. Upon arrival at the site, the floater is permanently moored for operational use. It is important to note that mooring lines and their anchors must be installed before the floater's arrival at the site. These installation steps form the main topics of today's presentation. Let me explain what Gentek did to ensure stability at each stage of installation process. As we discussed in the previous page, the first installation step is load-up process. In this stage, they use SPMT, which stands for Self-Propelled Modular Transporter, to transport the floater. For those unfamiliar with SPMTs, let me explain briefly. As you can see in the picture here, SPMTs are used to move heavy cargo, such as floater in this case. From an analytical perspective, the tire of SPMT act as a support point with a specific length. Structurally, these support points serve as a reaction point. From a hydrostatic stability standpoint, the weight of the floater is transferred to the bars through this point. At each step of the movement onto the barge, the weight distribution through the tires must be accounted for in the hydrostatic stability analysis. In MOSES, both structural stability and hydrostatic stability can be evaluated, taking into consideration the effect of SPMT. Once the floater is positioned on the barge, it is lowered into the sea to allow the semi to float using buoyancy differences. Gentek ENC mentioned that they did not perform this type of analysis during the initial design stage, but plan to include it in the detailed design stage. For reference, MOSES has long been used for similar analysis, such as casein installation from a floating dock or buoy separation from a barge. MOSES handles these analyses as a series of static analysis with varying ballast conditions and can optimize the ballast configuration for each step of lowering sequence. After the floater is loaded onto barge and separated, it needs to float in water. At this stage, the tower and rotor nacelle assembly are installed. During this process, the floater must maintain sufficient hydrostatic stability to ensure safe operations. To confirm this, hydrostatic stability was checked twice, once with and once without the tower and RNA. The goal was to determine the optimal draft and ballast condition that meets the requirement. For example, metacentric height, should be greater than 1 meter, and difference between water depths and the draft should exceed 2 meters. After verifying hydrostatic stability, mooring line forces were analyzed when the floater is moored at the quay, in what is known as quayside mooring analysis. And also, panda forces also computed. As shown in the image here, there are lines connecting the quay to the floater. And although not visible here, fenders are also present between them. The analysis focused on checking line tensions and fender forces during the contact. Similar to hydrostatics, this mooring analysis was conducted twice, with and without the integration of tower and RNA. Additionally, if necessary, MOSES can account for the effect of diffraction, wave diffraction, when waves interact between the quay and the semis submersible. In other words, hydrodynamic interaction can be modeled and considered in MOSES. After integrating the tower and RNA, the floater needs to be transported to the installation site. There are various methods for transporting it, and in this case, Gentek decided to tow it through the water, a process often referred to as wet towing. To ensure the safety and stability during the wet towing, a series of hydrostatic analyses were performed to determine the optimal draft. GM, the metacentric height, and the GG, the writing arm, curves were analyzed, taking into account the critical axis, since the semi-submersible is not symmetric. Time domain simulation was also conducted to analyze the dynamic tensions in the towing lines caused by tugboat. Dynamic tension refers to nonlinear behavior, such as when a slack line suddenly becomes taut, potentially generating extremely high tensions. These effects were captured during the simulation. Additionally, if the towing line is too long, the floater may exhibit the excessive motion perpendicular to the line, tug line. This phenomenon is known as fishtail effect. To prevent this, the towing lines must be appropriately sized. All these analyses were carried out using a single software, MOSES. Structural stability was also evaluated by identifying the most critical time steps based on the structural loads. For example, critical moments may occur during maximum floater motion or when towing line experienced peak tension. Load cases were generated for these critical time steps, followed by structural analysis and code check to ensure their stability. Once the floater arrives at the site, it must be permanently moored. During the wet towing phase, there is typically minimal ballast water to reduce the submerged portion of the structure, thereby minimize the drag during the journey. After arriving, the floater must be ballasted to the required depth for each permanent position. However, this ballasting process is not a quick task. It takes significant time. To ensure stability during the gradual sinking process, stability check must be performed at each ballasting step. This can be efficiently handled using MOSES, which even allows for automation of the ballasting sequence according to your specific requirements. At the site, mooring lines need to be connected sequentially, not all at once in this case. This means during the initial connection of a mooring line, 2 tugboats are required to support station keeping, designed to withstand a 1-year return period environmental condition. As additional mooring lines are connected, for example, when 2 lines are installed and a third is being added, only 1 tugboat may be needed for station keeping, as specified by DMV rules. For your reference, tugboat forces, variations in these forces depending on the pace and dampings can all be modeled in MOSES to enhance the accuracy of the analysis. We have reviewed the pre-service analysis so far. So now let's examine the technical issues encountered during this engineering process. The first topic is about wet towing and installing mooring lines, which requires the help of tugboats. To simulate the tugboats and lines in MOSES, we use the tug class. This lets us input the tugboat forces and pace angles relative to the wave crest position. So the forces change depending on wave's position. There's also an option to set the range of these changes using %_force. For the tug lines, we can actually model the physical lines connecting the tugboat and the floater, as you see in the image at the bottom. This helps simulate real towing scenarios. For forward speed, we can include it as a forward velocity in time, and in the frequency domain, we use the minus speed option when calculating the RAO. This adjusts the encounter frequencies of the waves during the RAO computation. Gentek ENC mentioned a couple of challenges. First, they think it would be helpful to have a feature to calculate the towing velocity directly from tug forces. While there's a workaround to do this, having it as a built-in feature would be more convenient. Another challenge they brought up is figuring out the best position for the tugboats depending on the different environmental directions. Of course, this can be done in MOSES right now. The next topic is structural analysis using time domain load cases. As you know, the rules usually recommend running simulations for 1 to 3 hours to capture the peaks in the system responses. By system responses, I mean everything we get from the simulation. I mean motions, mooring tensions, and so on. For wind turbine analysis, we typically run these simulations, then use the extreme values or statistical results for design purpose. These are based on a single time step or a value derived from probability calculations with data here. For example, let's say we are looking at the result of a time domain simulation. If we are trying to determine the properties of tug lines, we might just take the maximum value from this graph, from the values here. But if that feels too conservative, we could use statistics to analyze the data more thoroughly. That said, structural analysis is a bit different. We cannot just focus on one peak because structural failure might occur at another peak or even somewhere in between the peak and trough. I mean, we never really know. So offshore course includes rules to determine the maximum structural response for structural members. For non-ship shaped offshore structures, the common design load parameters assumes symmetry about an axis and require selecting specific time steps, such as when maximum split forces or pitch moment occur. A technical challenge arises in calculating these maximum split forces and longitudinal shear forces, etc., at each time step to identify the critical time step. MOSES does not directly support this calculation, but there is a workaround. MOSES can export applied load cases in SOX format, and using the SOX Python API library, we can post-process the joint and member loads in SOX to identify these forces and time step. We then back to MOSES and run structural analysis with the load cases at those time steps. This is a workaround to capture all these design load parameters. Gentek also carried out a fully coupled analysis for verification purpose, using MOSES' ability to interpolate with Bladed, the turbine engineering tool. Here's the workflow they followed. First, they create analytical model in MOSES. This included a panel model for dynamics, and structural model for structural analysis. Then they calculated hydrodynamic properties such as added mass, damping, excitation forces, and hydrostatic stiffness. These properties were exported in a format that Bladed could directly import, thanks to MOSES built-in export feature. Next, they ran the fully coupled analysis in Bladed using the relevant DLCs, design load cases. Afterward, the results from Bladed were imported back into MOSES using Templify, which simplifies and automates the importing process. Finally, they used MOSES to perform structural analysis and code checking with each additional functionalities. This is almost all about the engineering course Gentek did. And let me move on to the MOSES capability for floating wind turbines. The first feature I want to introduce is the integration with Aerodyn solver. For your reference, Aerodyn is an aerodynamic analysis solver within OpenFast, developed by National Renewable Energy Laboratory in the United States. It is an open source code widely used in the industry. It is now integrated with MOSES, enabling our users to perform the coupled analysis with aerodynamics. Here, we have made MOSES the master solver. At each time step, it sends the floating platform's position, velocity, and acceleration in the specified wave environment to Aerodyn. In Aerodyn, the entire structure's position is updated and the turbine allowed to rotate in the stipulated wind environment. The calculated rotor loads are then returned to MOSES where the forces are applied and the structure is moved accordingly. The data transfer is continuous, ensuring both solvers are constantly aware of what the other is doing. During this time domain analysis, it is also very important that we consider moorings. MOSES is more than capable of simulating many types of mooring systems, particularly those that might be used for wind turbines. In MOSES, we have several different types of mooring lines available for analysis. Some more complex than commonly available in wind turbine analysis tools. We also understood that single time domain analysis can take a long time to resolve. For example, a typical 3-hour duration turbine analysis is very computationally intensive. For this reason, we have developed some land grid tools that automate this process and run this analysis in parallel on an unlimited number of cores machines. This significantly reduces the total time to analyze. For this reason, we have developed some land grid tools. Here, multiple MOSES commanding profiles can be processed in parallel using the grid analysis in the MOSES executive. This feature can be used on a local machine, taking advantage of the available cores, or on additional machines on the local network, provided those machines have MOSES version 12 installed. When the grid analysis begins, MOSES executive will automatically display the grid nodes window at the bottom of the screen. Inside this window is a table that shows the machine on which MOSES is running. The commanding profiles running on that machine, the percentage of complete, progress, and any status report. The results from the job are sent back to the master machine and displayed in the project view, as if those jobs have been processed locally. The grid run feature is available in all licenses except the standard MOSES license. Note that the grid is restricted to the local machine only for the MOSES Advanced license. Your Bentley account must also have a current select entitlement. Last of all, let's review the workflow for the analysis of floating turbines. First, we need to build two types of analytical models in MOSES, one for hydrodynamics and the other for structural analysis. Next, we need to perform the hydrodynamics and hydrostatic analysis to compute key properties. Hydrodynamic analysis determines the properties like added mass, damping, excitation forces, while the hydrostatic analysis evaluates the properties such as floater stiffness in water. Once these analyses are complete, we proceed with coupled analysis using aerodyn. This step allows us to investigate the motions, mooring tensions, and structural stability, including the plate buckling and member code checks. If any aspect fails to meet this requirement, we revisit the process and refine the models as needed. This is the workflow MOSES has for the floating wind turbine. And this is all I prepared today. Thank you for your time.